Good morning from Colorado. This is Michael Dix with the marketing team, and I'm joined with Jarrett Fraser from the GNSS product team. So we have a good webinar for you. If you have any questions for us, go ahead and enter those in the chat box throughout the webinar, and we'll try to work those in during the presentation or try to answer them at the very end. And with that, I'll turn it right over to Jarrett.
Hello, good morning and good evening, everybody. My name is Jarrett Fraser. As Michael mentioned, I'm one of the product managers on our GNSS team in Trimble Geospatial. Today I'm going to share with you a presentation that we gave at Trimble Dimensions this year. It's about a test campaign we did some time ago, comparing Trimble receivers and some competitive receivers on our canopy test course. So I'll get started right away. So basically, typically we talk when we have a live room here about how long ago everybody started using GNSS. Can't really do the interactive thing right here with people in front of me, but the first on-the-fly initialization GNSS unit was the Trimble 4000 SSE back in 1994. Usually there are a couple people in the room when we give this presentation that have actually used one of those machines back 25 years ago now. And as you can see over the little timeline here, we've had Trimble has been involved in the innovations of GNSS, RTK technology for the surveyor over the years, with the first integrated receivers with the 4800 and then the full L5 constellation for GPS with launched in 2010 on the Trimble R8, and then Galileo, of course, the next year. And now we're all the way up to Catalyst, the software-defined GNSS receiver we have. So basically, when you're first using, in 1995, those initial launches of RTK, this is the kind of canopy that you would look at and think, all right, I better get the chainsaw on the total station. Today, we're getting better and better solutions in here. And this is actually a shot from our test course where we had one of the points. So you can see what kind of anecdotal evidence we have for what kind of canopy these machines will work in now. So just a quick agenda for the presentation, just a little quick introduction of what we did and why we're so interested in this topic, and then just go over the common source of GNSS errors, particularly ones that are present when you're doing work under canopy. A description of the test site, the equipment and the methodology we used, and then the procedures and the survey parameters we took into consideration when we were doing this to make sure everything was consistent throughout each run of the campaign. And then an analysis of the results that we get, and then a little quick summary, making sure we tie it all together at the end. So these are some shots, like I showed in that first image, where we were actually taking these shots for the test campaign. As you can see, there's quite a bit of dense canopy and coverage up above. So essentially today, as we all know, the GNSS users are expecting to use their equipment in more difficult environments, particularly forest canopy. Historically, you'd have to take a lot more time to get out your conventional total station and your chainsaw and cut line and just to get a couple shots in these environments. Now it's common that people want to just walk in with their receiver, get their shots, and walk out inside of 5 minutes. So these forest environments do introduce the challenging impacts to compute the position. There's a lot of multipath, there's a lot of weak signals because of the masking of the canopy, and you're getting intermittent signals when they're passing through dense parts of the canopy. And the higher uncertainty in the computed positions in both real-time and post-process GNSS affect the accuracy level. So everybody that works in the field basically experiences this, whether you're doing natural resources, oil and gas exploration, doesn't matter. If you're a surveyor, you're going to run into canopy at some point, unless you're in the middle of the desert or the prairies. And even then, still, it's possible. So users do have to balance in these situations the need to obtain that solution with the desired precision that they need for their job requirements, and accepting solutions that have precisions that don't meet those specifications. So time of the job you need and the ability of being able to do it as precisely as possible are two considerations that a user is doing to make sure that they get what they're looking for their deliverable. So the widely varied results and performance under canopy described by the manufacturers and users is kind of inconsistent. It's really hard to test for how it performs in canopy, since it's impossible to model in advance every single possible canopy situation that a user can encounter. So the in-field estimates of precision provided by the GNSS receivers are often a little bit optimistic. And a lot of this information is, of course, anecdotal. Sometimes you can go out in the same course, depending on the geometry of the satellites at the time, and get completely different levels of accuracy with the same receiver, same software. So for this, we needed as much empirical data on RTK performance as we could get with multiple receivers and under controlled conditions. So we tried to do it as objectively as possible with Trimble and competitor solutions under the exact same conditions in the exact same course at the exact same time. So we developed our data on known coordinates for the accuracy of the measurement. These are all shot with total station tied to geodetic control. And we compared the precision report in the field against the accuracy that was actually done when we analyzed the results, and compared the time required on the point to achieve a specified position. I have a little bit more on this methodology later on about how we actually made sure that everything was consistent. So now I'm going to just go over a couple of GNSS errors. This will be back to surveying 101 for a lot of people, but there are some things in here to really consider when you're taking shots under canopy. So the satellite orbit and clock errors directly affect the satellite range measurements. That's pretty common. That can happen under any situation. And then you have the ionosphere, which is got issues with getting the signal through. It's that altitude of 50 to 1,000 kilometers, and sometimes in some parts of the world we have scintillation, which affects it even greater. The troposphere, which also causes a slight delay. And then multipath, of course, signal bouncing off other objects nearby. And then signal masking, which is the most common for canopy, which is when obstructions block the signal and degrade the measurement accuracy. So there's a little table here we have to just show you how much each of these types of errors can affect your position. These are obviously extremes in some cases, but when you tabulate them all up together, there's often a couple centimeters at least of error when you're in situations where you have canopy above you. So just a brief overview of how multipath occurs. It's multiple copies that are created when the satellite signal reflects off of objects near the antenna. Happens a lot with glass buildings or other such obstructions. It'll basically be getting multiple signals from the same satellite, and they'll be in the order of nanoseconds apart sometimes. So that can be quite a bit of additional error added to your solution. So just moving into the actual test we did. So this was conducted in the western U.S., not far from our Colorado offices. It's a test site with good coverage from a regional real-time GNSS network based on Trimble VRS technology. The closest physical reference station of the actual real-time network was approximately 14 kilometers from the test site, and it was used for single baseline measurements as well for the long-range ones. We also did have a CORS receiver mounted approximately 5.5 kilometers away that we used for the short-range baseline measurements. We had good weather. It was windy during some sessions, which wouldn't affect in an open sky anything, but it does blow the trees around a little bit, so it makes the signal more intermittent. And then on the test site, we had 5 groups of points. Each group, there was 4 points that were put in the forest in medium and dense canopy. So that photograph you're looking at your left was taken directly from one of the groups of control points. The fifth location was near the forest, but in the open field. If you look in the right photo, it was over close to the road, so that you had a unobstructed view to the sky. That point out there served as the control and the initialization site for the test. And yeah, the view that was obviously just one of the points that we have the view on the left, but I think those other views that I showed earlier in the presentation were all from specific point locations. So they all kind of look like that. They're all pretty dense. So we set up these multi-color-coded markers at each location with inside of a 2-meter radius. So during the measurements, each brand of receiver occupied the same marker for every measurement. So we did the measurements simultaneously under identical conditions. So they were getting everything, even the little slight wind breezes were the same during these locations and procedures. So the coordinates for all the markers established, we're using total stations tied to geodetic control, as I mentioned before, in the NET 83-2001 Colorado Central Zone 0502 datum. So equipment, we had a variety of receivers and accessories. We had current Trimble models, and we had some models from 2 competitors. All receivers were all-in-one configurations, meaning the top that each manufacturer offered. They're all smart antennas, so no integrated receiver tied to an external antenna or anything, all integrated. So, and they all had the current GNSS firmware and field software from each specific manufacturer, and the receivers were mounted all on 2-meter fixed height range poles with bipods. Some of these occupations were a little bit longer, so you didn't just want to have them held by a user for multiple minutes. So the test team was all experienced surveyors, engineers, and technicians, and efforts were made to prevent operator error or bias from influencing the results. So all test teams were trained across the board on all receivers and all field software and all data collectors they were using. So the procedures and parameters of what we actually did during the test. So the measurements were conducted using RTK via cellular. This was done because we did not want to introduce another source of error to propagate through with the UHF corrections, because the area wasn't really conducive to real good UHF signal. It had great cell coverage, so we made sure that everything used the exact same, tied to the same network. So we did that single baseline and long range and single baseline short range to those 2 stations I mentioned before, the 14-kilometer and 5.5-kilometer ones. Then a network solution, long range, that was basically temporarily removing the closest reference station. And then a network solution short range that did also add a close by reference station. So the receiver configuration was set up so that it would automatically record a point when it achieved a precision of 7 centimeters, which is typically acceptable in canopy for the workflows and deliverables you're doing if you're not going to get at the total station, in horizontal and vertical both. And the sessions were conducted over a 10-day period where we did 2 sessions each day, a morning session and an afternoon session, to get data under different weather conditions and to make sure we had enough redundancy. I don't know if you can ever have enough redundancy, but 10 days to 20 sessions is pretty good for the purposes of our test. So essentially, we would initialize the receivers under the open sky on that known control point that was out by the road to make sure everything's working and communicating properly. We then move the receivers into the forest and occupy all 4 points 4 to 5 times each session. So 5 points were measured for each occupation. For each occupation, the operator would wait until the receiver obtained the desired position, followed by recording the point and the time and the displayed position. Now, we did have a final amount of epochs that they would take. If the observation time took 300 seconds, it would force stop the point and collect the associated data. Point 1001 in the open sky was measured after each loop, doing 4 or 5 check shots per session. So the analysis and results. So that was a lot of data, as you can understand, doing multiple receivers, 20 campaigns with all those shots. We had 1.16 gigabytes of field data and more than 300 HTML files for reports and analysis. So it was checked and downloaded at the end of each day, so we were kind of doing it simultaneously to when we were doing the campaign. Each observation session was analyzed separately. We had receivers giving observations, and each one was compared to truth for all 4 points under the canopy. We calculated the average error for all observations to establish a mean for the horizontal and vertical error for each receiver and for each of the 4 observation types. And the average error for each receiver on point 1001 was calculated separately to just make sure we had a baseline for control purposes in the open sky environment. And then we compiled the results, we averaged the values for each point and were computed for each session. So that was typically 20 some odd occupations with multiple observations on each point. So first off, we'll start with the single baseline, the short range. So as you can see, there's the blue diamond is Trimble, the red square is one of our competitive systems, and the green triangle is the other competitive system. So this was fairly consistent, just showing that the short range baseline gave a bit better results than some of the other ones. But you're still looking at up to 10 centimeters of error on some of the points. So this is what we measured and was reported in the field versus the actual truth. So the single baseline on the long range point got a little bit worse for some of the systems. Still tightly grouped on the VRS version of that, but there was for the single baseline on long range, it was a little bit starting to show the effects of the canopy. So this set of plots depicts the performance on each system for the long range VRS measurements. So this is where you start to get a little bit less of a grouping. So the precision of the system A and system B, it's kind of scattered. There's not a whole lot of consistency to where the shots are registering. If you look at the Trimble position, though, there's a pretty tight grouping with just one outlier. So the error for each point's measured coordinates compared to the known values. This graph is just showing a couple different things on the different axes. So if you look on the left side of the y-axis, that's showing the error in meters, and the right side on the y-axis is showing how much time on the point it was. And then, of course, the bottom x-axis is showing each manufacturer. So while System A got its shot a lot quicker than Trimble in System B, it was actually quite a bit of horizontal error, well outside of the acceptable amount. And then for the long range, it was a little bit closer with when they were actually getting their accepted precision. And again, there was a lot of consistency in the Trimble units between the single and baseline long range and single baseline short range for accuracy, but there was a little bit of vertical error increase in both of the other systems. So VRS, moving to the full network, the short range version, we had a real good results with the Trimble system, both in fix and level of accuracy. The other two systems were kind of more consistent with what they were doing for the single baseline. When you moved it to long range, we had a little bit tougher time getting a fix with the Trimble system, but the accuracy didn't degrade as much as it did with the other System A. System B actually performed, although it took longer, it actually performed a little bit better in accuracy and time to get the precision. So the accuracy and the reported precision. So we basically did a simple test on the reported precision. The graphs present the percentage of measurements that had passing scores. We defined a pass as an error that was less than the reported precision plus a centimeter, and a fail was an error exceeding the reported precision by more than 1 centimeter. So basically it was an analysis to see how well the receiver is actually reporting the precision that it's getting under canopy compared to the truth. So all of the receivers tested weren't getting anything close to 100% of what they're supposed to be reporting. But if you look at these on the horizontals and verticals both, the Trimble system did have a higher percentage actually getting the pass. And that goes across the board of all 4 different measurements: the single baseline, long and range, and the VRS long and range, long and short range. So to summarize, so essentially one thing that our test really showed us was that it just confirmed the difficulty of achieving reliable and accurate results when you're using your GNSS receiver in dense forest canopy. The accuracy and productivity both suffer when trees and foliage obstruct the access to the satellite signals. And the data does indicate that the Trimble solution provided an advantage in collecting points over the course of the project. So that's not only the superior performance and accuracy, but more consistent reported precision estimates compared to the actual accuracy of the measured points. So we all know that this is only going to get to be a bigger and bigger use case for people using GNSS receivers. The users will continue to push the technology into the difficult environments, whether that's canopy, whether that's urban centers, whether it's obstructed shots that you would traditionally use a total station for. It's something we're going to continue to see. The knowledgeable users do understand that you generally have a lower percentage of accurate points measured in those areas, and they generally avoid working under such conditions unless they absolutely have to. In the instances where you must use RTK under canopy, the field practices to get your optimal measurements while understanding the results will not approach the performance or obtain those open conditions are kind of used. A lot of people will tape offsets. There's a couple other methods that have been successful over the years to just save you the time of getting at your total station, but do reduce your accuracy a little bit. And the data does indicate that the Trimble solution provided an advantage in collecting points where users must operate under canopy. It had superior accuracy performance, both horizontal and vertical. The time on point was similar or better than the other solutions. In some cases, the other systems did have less time on the point, but the actual reported accuracy was not as good as what it was supposed to be, and they did have pretty big diversion between what was reported and what was actually the truth. So the Trimble solution did outperform the competing systems in the ability to provide field reported precision estimates with a lot more consistency and a higher level of actual accuracy of the measured points. So at that point, I think it's time I can turn over for some questions. If anybody has anything they would like to ask, Michael, see any questions coming in?
Yeah, so we got one from Rob about can you tell us which Trimble receivers were used? And then also, are you able to tell us which of the brand A and brand B products were used?
So it was all the Trimble, the current Trimble RTK receivers at the time, R10, R8S. With brand A and brand B, to tell you the truth, I'm not actually even sure, but we're not really in the business of reporting what competitors were doing what. So I don't have an answer for what they were. They were major competitors for sure.
Got it. Okay. Did you notice any difference in the R10 versus the R8S and canopy? Or
the R10 and the R8S, there was difference in between shots, but it was mostly aggregated, so it was hard to tell what was coming from what. But there weren't really many outliers in the data compared to the brand A and brand B, so it was less apparent. But it was just the R10 and the R8S.
And is there any best practice you'd recommend from what you saw in the single baseline results versus the ERS? Would you, like if someone was doing a topo and canopy, would you recommend them to use either of those? Or?
Well, VRS is gonna give you a better network. But the main indicator of the test were the shorter the baselines, the better.
Okay, so even shorter single base.
Yeah.
Shorter.
Yeah.
Got it. And on some of the differences in the error estimates that you saw versus the actual true results, is there also any best practice you would recommend for a surveyor going out in canopy, knowing that the error estimates might not be completely true? Should they just try to test on control and, you know, kind of see what the error estimates are saying versus true? Or?
It's typically in surveying in general, redundancy is better. So just more shots, the more better it is, so that you can get an idea, aggregating the points, so you know a better idea of what the actual truth is, or how close as you can get it. There might be some sort of systematic error that's offsetting it some, but if you go out and do multiple shots or do longer occupations on shots, it'll help eliminate some of that. And of course, when you're doing multiple shots, you might have different conditions that are changing it, so it might not be as bad if you do it an hour later.
So it's constantly kind of fluctuating. Okay. And you were kind of in the summary talking about the Trimble advantage. Using Trimble receivers gives you an advantage in canopy. Is it possible to like quantify that? You know, if our distributors are talking to customers about canopy and how Trimble performs better, is there like a performs 10% better, or does it make sense? Like, is there a way we can quantify that, or is that too hard?
It's really, I don't want to say impossible, but it's really difficult to quantify things that are so impossible to model in the future with what canopy is going to do. So we all we can really do is put in different algorithms to mitigate the effects of canopy and multipath and everything else. So the more constellations in the sky and the more satellites that are up there being tracked and used in the solution, you're going to get better redundancy. So you might have a path through this masking canopy to a satellite that you wouldn't have had, you know, when it was just GPS up there with a handful of satellites being used. So there's that aspect, and then how modeling what we do with that signal when we get it. That's really all you can really do. You can't really set a spec of how it's going to behave in canopy. It's really, you know, we have our receivers, and our competitors also have their receivers spec'd at performance in ideal conditions out in the field with full coverage, good times of the day, good areas. So it's not really something we can quantify. We can do tests like this all the time, and they're going to give, you know, different results. But the more redundancy we do, the better we can show that the Trimble systems perform a little bit better.
Yeah, sounds good. Got a couple more questions here. I think there were still just some questions on the Trimble receivers used. So was it the R10 and the R8S? R10
and R8S were the Trimble systems, yeah.
Okay.
And the systems A and B did have identical specs, essentially. A lot of, if you look at the data sheets of Trimble receivers and competitive receivers, the specs are very, very, very similar, if not identical. And we made sure to, you know, we weren't putting an R10 versus the entry-level sub-meter receiver for a competitor or anything. It was the equivalent of an R10.
Got it. That makes sense. How many, or I guess we're using how many GNSS constellations?
So the constellations, we used everything that was available in the sky for everything.
Okay. So a couple more questions, I guess, on constellations. Do you know if Trimble has done any testing in other parts of the world that might pick up different or more of, you know, the different constellations?
So to my knowledge, we haven't done this. It's a very exhaustive campaign, and takes a lot of resources to do, a lot of time, and a lot of person hours to do it. So, and then of course getting competitive equipment and shipping that around. So we haven't done this more than this one time. I'd like to get it done as much as possible, but there are some limitations in how we can do that. But yeah, the next step will probably be to do it here again. This is a couple of years old now, and then hopefully get resources to do it somewhere else.
most of the questions. If you have any more that you're thinking of, go ahead and type those in, and we'll get to those. Maybe one more question in terms of, different types of tests or more types of tests. Would you recommend that a Trimble distributor perform some of these tests just to get more familiar with how Trimble works in their canopy, get their own kind of understanding of it? Was it helpful to kind of go through this and see that?
It's definitely really helpful. I'm sure that everybody has the resource constraints that we have, so it might be difficult for them to do, but it's definitely helpful to see the results that it actually gives, and especially when compared to truth. And it's pretty eye-opening to see how far outside of what the actual reported accuracy is and what the actual truth was. So that some of those competitive systems, they have quite a big discrepancy there, and realistically, I don't think there's really much you can do other than just test it yourself. There's the data sheets all kind of say the same thing, and canopy's hard to model in advance, so it's definitely helpful to do it if you have the opportunity and the time and the resources.
Good. And then just a question, have you tested any of the Spectra receivers? It sounds like this is just Trimble, and
yeah, there were no SP60s or SP80s used. I would like to include them in the next round. We would have Trimble, Spectra, System A, System B, and possibly Systems A through or C through Z, but we haven't done anything with the Spectra products yet, but hopefully next time.
And so someone had a good suggestion from Jacob of maybe doing the mapping grade solutions. Products used more for GIS, I guess, just seeing how they would work. I know a lot of GIS field work is done.
Yeah, I'd like to see that too. We have that canopy test course, so it's a matter of just getting the availability to do this. Realistically, I'd like to be doing this every few months with every time we get new competitive products and everything, but the reality is it's just a very, very exhaustive process that takes a lot.
To get enough data to really understand.
I mean, we had over a gig of data, and the average observation is in the order of kilobytes. So
still some more questions on the constellations. Baidu and Galileo, are they really giving an advantage, do you think?
Yeah. Anything out there, as long as the signal is healthy, is going to just add to that level of redundancy. And if all your GPS and GLONASS satellites, depending on the geometry of the sky, at the moment you're taking the shot, they might be mostly masked, and there could be a chance that where the Baidu and Galileo are sitting might have a better path to the receiver. So it's really hard to predict. You can look at your sky plot and see where everything's going to be, but you can't really measure that to the degree of where that particular branch is sitting in relation to it. So the more constellations and more satellites you're using, the better your result and redundancy is going to be.
Good. Was that the R10 Model 2?
This was done before the Model 2 was released.
Okay.
So we just had R10 Model 1.
Initial model. And statistics question from Tommy. Do you know the confidence level compared to the in-field estimates?
It was all 1 sigma.
1 sigma?
Yeah.
Okay. With the mapping grade, the Catalyst receiver and antenna would be interesting to see how that performs as well under.
Yeah, I know that we did test the DA1 using Trimble Catalyst in that same canopy test course when we were doing pre-release testing. I don't know what the results were, or I don't have any of that data, but I do know it was ran on the same course. We typically will run all of our receivers on this in some regard. We just won't do the exhaustive test parameters that we did in this campaign.
All right. I think that's most of the questions for now. Anything else on the wrap up or?
No, just we look forward to doing another one of these tests. Hopefully we get to do multiple, and hopefully we can get them outside of the US even, and maybe do some mapping grade receivers. And I hope to have another one of these presentations and update in the future.
Oh, good. Well, thanks, Jarrett. And this recording of this session will be automatically emailed out, should get to your inbox tomorrow. Whether you attended or even if one of your colleagues registered and did not attend, it should still be emailed out to you tomorrow. So thank you for joining and thanks for your questions. And we'll talk to you guys soon.
Thanks, everybody.